Hello and welcome back to Class Time, your daily classroom for CSEC and CAPE students. Watch this lesson while on the go, in real time, on Television Jamaica's YouTube or One Spot Media.
Have questions? Send them to Television Jamaica's Facebook page or Instagram at television_Jamaica using the hashtag TVJClassTime. Today, we will be doing mathematics, looking at circle theorem. I am Tyrone Brown.
And I am Brittany Henderson. We'll be your teachers for today. So let's get started.
Okay, so Brittany, I'm having a problem. This whole circle theorem, it's a bit confusing. Can you help me out?
Boy, I don't know if I can, but let's try. So today we'll be looking at circle theorem and we'll be exploring some of the concepts used in circle theorem.
In today's lesson, we'll be exploring some of the concepts in circle theorem. So let's start. Let's first take a look at a quick recap in regards to the parts of a circle. Can you identify the shaded parts of the circle?
All right, so you wanted me to help you. Let's see if I can. Let's see how much I remember. All right, the shaded parts, okay, inclusive of the outer sections I see. So I think this is the section here. It's a part of my circumference. So this section here is a part of my circumference, and I believe it's called an arc, right, Mister?
Yes, I think that is what it's called, I think
Okay.
my teacher said it's a part of the circumference, so it must be the arc.
Okay, and as I mentioned before, the boundary of the circle is the circumference. Let's see what else we could identify.
Right there in the middle of the circle.
Okay, so there's a center point in the middle of the circle, and there's a line that runs through, runs through the center of the circle, and it touches the circumference at 2 points. What's that called?
I believe that is the diameter.
All right, so we also have the diameter, and half of the diameter is known as our
Radius.
radius. Okay, so it looks like we're remembering a lot of things.
I think we remember
right?
a lot.
All right,
I
anything
think
else?
this green area down here is called a segment. And because it's the smaller segment, I would think it is the minor segment.
Okay, so we have a minor segment as well. How about that red section there?
That one is tricky. It's bounded by 2 radii and the circumference, so I think it must be a sector.
All right. So guys, I wonder if you at home, you were identifying the shaded parts of the circle. But let's check and see if our answers are correct, because I'm a little bit, not so clear on what's happening with it. So let's check.
Okay, so we did identify the circumference.
Awesome.
And we said it was the length of the boundary of the circle. And it's also called the perimeter of the circle.
All right. So awesome. We're going all right so far. The diameter. And the diameter, again, is the distance across the circle, passing through the center of the circle and touching the circumference at 2 points. So far, we're 2 out of 2. Let's go again.
Question, before we actually move on, what if it doesn't pass through the center? Is it still going to be a diameter?
Well, according to our definition, that would not be a diameter. So if it doesn't pass through the center of the circle, it's not a diameter. What is it called?
I think we'll talk about it a little bit later. I think there are some notes on that.
Okay.
Let's see.
All right, so we also identified the radius earlier, and we did say the radius is the distance from the center of the circle to any point on its circumference. So here we have the radius.
Oh, I'm seeing this touching 2 parts on the circumference, but it's not passing through the center. So it's a chord.
So when it is that we have a line that touches 2 parts of the circumference, not going through the center of the circle, it's a chord.
It's a chord and not
A diameter.
it's not always a diameter.
No.
Okay.
The chord is it a special type of diameter? Is it special or no?
Chord? The diameter, if I can recall, is the longest chord.
Okay.
So it's a line joining 2 points on the circumference. And it splits the circle into 2 segments, a minor segment, which is a smaller portion, and the major segment, which is a larger portion.
So I remember you talking about this earlier. Awesome. So far, guys, we're on track. Everything is right so far. Look at that. Now, the very first thing that I identified when we started was actually the arc before I talked about the circumference. So the arc is a part of the circumference of a circle.
Oh, I'm seeing a special line here I haven't normally see on a circle. It's called a tangent. Can you tell me a little bit more about the tangent line?
All right, well, according to our definition here, the tangent is a line which touches a circumference at one point only. So it only touches our circumference at one point. From the Italian tangere, to touch.
Okay.
I hope I pronounced that correct. You know, I'm not really Italian, but I try.
Okay, and the most important thing, it can only touch at one point, because
Only one
if it
point.
touches at 2 points, it's no longer a tangent.
If it touches at 2 points, it's no longer a tangent. That is correct.
Okay. What would you think it would be, though?
2 points?
If a line touches the circumference at 2 points?
Yeah, I don't know, sir. You tell me. What is that?
I think that might be a chord.
Oh, yes. You said that earlier. Guys, I hope that you're not like me and you're actually paying attention, because I totally forgot that sir said that it was a chord before. Don't.
Okay, let's see what happens. So, we went through the parts of a circle, and now we're going to take a quick recap on some of the core principles that we would have learned when working with triangles. And that is important because we often use these shapes when we are solving problems for circle theorem. Let's put up the first one.
Okay. So here we have a triangle. Mr. Brown, what type of triangle is this?
I'm seeing a 40, a 90-degree angle, that's a right angle. So I'm thinking, since all the angles seem to be different, it's a scaling.
You sure about that?
Yeah, because once there are different angles, there are no angles in the triangle with the same value, it can't be isosceles and it can't be equilateral, so it has to be scaling.
Okay. All right, so we're asked, what is the size of the angle marked B? So guys, what do you remember about triangles? Is there anything that you know about the angles in a triangle? You know anything, Mr. Brown?
Oh yes, I remember a teacher saying something about the angles in a triangle summing to 180 degrees.
Awesome. So we know that the angles in a triangle should sum to 180 degrees. Now, here we know 2 of the 3 angles in our triangle. So do you think that you could find the value of B? I'll give you a second. I hope you have out your paper and your pen. Tell me the measure of angle B.
I'm sure they're able to do it.
All right. Let's try. So 90 plus 40 degrees, 90 degrees plus 40 degrees would give us?
I think that's 130.
130 degrees.
130 degrees, yes.
130 degrees from 180 degrees would leave us with?
50 degrees.
So the size of angle B is actually 50 degrees. Awesome sauce. Good job.
Okay. Let's look at another one. What type of triangle would you say this is? Oh, it's actually stated.
Okay, so here we have an isosceles triangle. So as you know, with isosceles triangles, Mr. Brown, what you know about the isosceles triangles?
I know 2 angles have the same measure as well as 2 sides have the same length.
Okay, awesome. So as you can see, we're going to find the value of B, which are the angles which have the same measure. So we know that one angle measures 40 degrees. Guys, again, it's still a triangle, so we know that all the angles in a triangle measure 180 degrees. Don't worry, I'm going to give you just 1 minute because I know that you guys can just do this in no time. 1 minute, work it out, have out your paper, tell me what the size of angle B is. All right. You think they solved it, or that's too short of a time?
They should be able to work it in that time. But
Okay.
let's see if we can help them out if they're having challenges.
All right, so I think we're ready for you now, right? So let's go. We know one angle so far, which is 40 degrees. So 180 degrees subtract 40 degrees would leave us with what, Mr. Brown?
That would leave us with 140 degrees.
140 degrees. Okay, and now we know that we have 2B. So we have two angles that are missing. So we're going to now divide 140 by 2. So that would give us what?
Hold on, why would we need to divide by 2?
Because we are trying to find the angle of B, and we have two B's that are missing, right? So we have B degrees plus B degrees. Remember, we're trying to find everything. So everything in this triangle should add up to 180 degrees. So it's 40 degrees plus B degrees plus B degrees. And we know that from algebra, B plus B would give me 2B.
So
right?
the value of these two angles that are missing must be the same.
They're the same measure.
Oh, okay, that makes sense.
Okay, so that's the reason why we're dividing by 2. So it's 140 divided by 2, and that would give us?
70.
So, great. The value of angle B is actually 70 degrees. So both of our angles here actually measures 70 degrees. I hope that at home you guys are working on it and you got it correct, right? All right.
That sounds awesome.
Let's try another. Okay, so
let us move into our circle theorem. And let's start with the first one. Here I am seeing something peculiar. There is a shape that is inscribed in the circle, but I'm noticing something there. What can you tell me in regards to the angles that you are seeing on the shape?
okay. The angle closest to the circumference measures 60 degrees, and the angle at the center of my circle measures 120 degrees. Now, if my math is correct, which sometimes it's not really so correct, but I think 120 degrees is twice 60 degrees. So I'm noticing that the angle at the circumference and the angle at the center of the circle, the angle at the center of the circle is twice the measure the angle of the circumference of my circle. That's what I'm seeing. I'm also seeing an arc.
You're also seeing an arc.
Yeah. My favorite thing to notice, guys, the arc.
Yes,
Rest,
DC.
I'm also seeing the arc.
And the angle at the center is formed with the arc.
Yes, I'm seeing that as well.
Okay, okay. Let's see what would happen if we change the values of these figures.
Ooh, computer magic.
Wow. I'm hoping that you are picking up something as the figures change.
Guys, are you seeing what I'm seeing?
I hope they're seeing it.
So I hope that you're seeing that there is something happening with the angle at the circumference and the angle at the center of my circle. Right?
And one of the things I was seeing, I hope you're seeing the same thing, is that the angle at the center is always half. Angle at the center is always double the size of the angle at the circumference.
Yes, I'm seeing that. So each time as you increased the arc, so as it got bigger, I realized that the angle at the center and the angle at the circumference also changed. So yes, I'm seeing that there's a relationship between the angle at the circumference and the angle of the center of my circle. And that one is twice the value of the other.
And that relationship holds true for all the cases that we would have seen
Yes.
In our example. And this one, our final, is a special case, and I'm hoping you're all seeing it at home. Can we identify what type of triangle this is?
A right angle triangle, is it?
Yes, because I'm seeing that 90 degrees, right?
Yes.
And I'm also seeing something peculiar about the arc.
Oh,
That arc is a special arc.
The arc looks like the semicircle. It looks like it took up half of. No?
Yes, it seems like a semicircle,
Okay.
right? So the sector is a semicircle, right? And it's bounded by the arc DC, which is 180 degrees.
And that's my diameter.
And
right
that is your
there.
diameter, yes. So once it is that you have the diameter being your chord, then the angle at the center is going to be a special value. And that is going to be a right angle valuing 90 degrees.
Okay. So I hope you guys are taking notes at home, write down all of these little things, right? Because it will come in handy later on. All right.
Okay. So let's see if we can formalize that for our students. So we realize that the angle that's formed at the center is always twice the value of the angle that is at the circumference.
All right.
Consider the two angles which stand on the same chord, and we notice that the angle at the circumference is half that the one at the center.
All right, so we say that if two angles stand on the same chord, then the angle at the center is twice the angle at the circumference. No, guys, we put this here just for you to take it down to ensure that you have these notes. So when you're revising, you can draw back for your notes. Okay, guys?
Okay. I'm hoping they got it.
I think they did.
And the angle, which is an arc of a circle, subtends at the center of a circle, is twice the angle it subtends at any point on the remaining part of the circumference. And that's another way of saying what we had indicated before.
So repetition is good, and you can see these definitions come in all different forms. It is important that you're exposed to everything.
Okay, let's look at a question, two questions.
All right. So, guys, I hope again you have out your paper, you have your pens, right? And I want for you to try these two questions. So, on the board, we have two circles. The first, you notice at the center,
The angle
measures 122 degrees. And the second circle at the center, the angle measures 129 degrees.
28.
Oh, my bad. 128 degrees, right? So, guys, I want for you to tell us the measure of angle A and angle C. Give you a little time, because I know that you guys are so excited. I'm going to give you a little time. 1 minute. Easy breezy. All right. You ready? You ready, Mr. Brown?
Okay, I am thinking that angle at the center for the first problem is 120 degrees. And as we already established, 122 degrees, sorry. And as we established before, the angle at the circumference is half the angle at the center when it's subtended from the same chord. Therefore, that angle, I'm thinking it's going to be 61 degrees.
All right. So how we get the 61 though, Mr. Brown?
half of the 122 or divide 122 by 2.
Oh, that is true. So 122 divided by 2 is 61. Yes, you're right.
Yes,
You're
yes,
right. So it
yes.
is 61 degrees. So angle A measures 61 degrees. So how about angle C?
I'm thinking it's the same, looking almost the same in terms of the angle at the center and the angle at the circumference having that special relationship. And we're given the angle at the center being 128 degrees. So I'm thinking we're going to need to find half of it or divide by 2.
Okay.
And that is going to be 64.
Yes. So awesome sauce. Mr. Brown is on top of the maths, right? So it's 64 degrees. So guys, I know that this was no challenge for you. 1, 2, you just do your thing, you just match it up. So I'm so proud of you guys. I hope you got it correct. And if you didn't, what's the thing with math? Practice really does make perfect,
Yes,
or makes improvements.
Yes,
So
it really
continue
does.
to revise your notes and look over and try again, right? All right, so let's go on.
Okay, so let us look at an exploration for another one of our core theorems. But first, before we begin, what are you noticing so far?
Noticing. Okay, guys. So you see a little pattern with me. The first thing I notice is the arc. So I notice the arc CD, right? So
Yes.
on my circumference, I notice my arc. So I see the arc first. Okay. The next thing I'm going to look at, and the next thing I see, is I realize that this time around, we have 2 angular measures at the circumference, and both of them measure the same thing. So I see angle E measuring 54 degrees and angle F measuring 54 degrees. I wonder why.
And they're subtended by the same arc.
Oh yes, and they are on
Yes.
my favorite part of the circle, the same arc. They're on the arc, yes.
Okay, let's see what happens next. If we put another one there. Wow.
How comes it measures the same? You guys saw
It's the
that?
same 54.
Wow.
So all of them are subtended by the same arc and they're all measuring 54 degrees. Let's see if we change the arc length. I'm hoping you're seeing what I'm seeing. As I increase the arc length, all of them increase to be the same value, maintaining the same value. But if I change one from the major arc and I put it on arc CD, it now changes. So you're seeing it is no longer 48 once the arc has changed.
And it's also in another segment, right?
It's in another segment as well.
Wow. Guys, I hope you're seeing this stuff. Wow. I didn't know. Wow, okay. Wow, okay. So sorry, you're teaching me some things today, You're teaching me some things.
So the most important thing is that they're in the same segment and subtended by the same arc.
All right, so in the same segment, subtended by the same arc, the values are the same. The angular measures are the same. That's what you're telling me, right, Mr. Brown?
Yes.
All right, guys, so I hope you took notes of that, right?
Okay, we're going to pause here. More mathematics after the break.
Welcome back to Class Time, your classroom for CSEC and CAPE students. If you're just joining us, we're looking at circle theorem. Now let's have a little recap. So Mr. Brown, take us through what it is that we were doing in the first segment, please.
I think we were discussing as regards the angle at the center versus the angle at the circumference.
Okay. And what's so special about the angle at the center of a circle and the angle formed at the circumference of the circle?
Okay, when we were having that discussion, we said that the angle at the center that's subtended from the same arc, right, it is twice the value of the one that is at the circumference. And there's a figure right here for you to do the analysis. I'm hoping that you notice that that angle at the center is 180 degrees and half of it is 90 degrees.
Yes, I'm seeing that. So I'm seeing where the angle at the center of the circle is 180 degrees and the angle at the circumference of the circle is half its value, which is 90 degrees. All right, so did we look at another theorem?
Yes, we went on and we looked at the angle subtended by the same arc.
All right, so we were right here, guys, before we left. So we're looking at angles subtended by the same arc. And we did a little experiment to start off with. Now, just a quick walkthrough. What happened when angles are subtended by the same arc?
Okay, we realized that once it is standing on the same arc, right, in the same segment, then the values are going to be the same, as is right there, 48 degrees. But once it is that we change the position of our diagram to ensure that the angle now stands in another segment and on a different arc, the value changes.
Okay. So guys, I remember saying to you before that I hope that you're taking notes. All right.
So we can pick up from here?
Yeah, man, we can move on. I think they've got it. Right, guys? You've got it.
Okay. So let's look at a question. I hope everybody is seeing it.
All right, so this is just for some more emphasis. So an angle that sits on a chord does not change the apex, does not change as the apex moves around the circumference, right? So we just discussed this a while ago, but again, repetition is key.
Formalizing what we had discussed earlier. And as we said, as long as it stays in the same segment.
Which is a crucial point. So it's very important that you note this. It must reside in the same segment. So as you saw from before, if the segment changes, the value of that angle also changes.
And we'll discuss further what happens in terms of that. And we can say angles subtended by a chord in the same segment are equal.
All right, guys. So note it. Same arc, subtended, angle subtended by the same arc, equal. So that's our theorem.
Alternatively, we can say angles subtended by an arc in the same segment are equal. Okay, so let us look at an example. Are we able to find angle A and angle B given the information that we know and the discussion we had earlier? Can you help me out a little bit, Brittany?
Oh gosh, guys, I hope that you're paying attention, because sometimes, I'm not really paying such good attention. All right, so let's see. You said to me that angles subtended by the same arc are equal. So looking at this diagram, I'm asked to find angles A and angle B. All right, let's see. I'm going to take a guess, Mr. Brown. Don't go too hard on me. All right, so I'm going to guess and say that angle A measures 20. No, angle A measures 44 degrees.
44 degrees. Why would you say that, Brittany?
Because I remember you saying that angles subtended by the same arc in the same segment, and if I'm looking at this right here, within the same segment, it should measure 44 degrees. Now, Mr. Brown, break it to me softly. Am I right or am I wrong? Right or am I wrong? Mr. Brown.
Yes,
Imola
you're right.
smile. Okay, good. All right.
Okay.
I was nervous there, guys. I was really nervous.
All right,
Right?
let's see what's happening with angle B.
All right, angle B. You think you can trick me? I already got this. I got this. So if this angle A down here is subtended by the same arc and measures 44 degrees, then Mr. Brown, 100% with confidence, angle B measures 28 degrees. Talk to me nice, yes?
You're definitely right.
Guys, I'm right.
You got this. You got this.
All right. I hope that you're getting it too at home.
Okay. For those who are doing it at home, right? She got angle B to be 28, and we can put in an imaginary chord because sometimes CSEC doesn't really give us the chord. So you can put in an imaginary chord if it is that you need that to do your analysis. And we can do the same thing for angle A.
Okay, awesome. So we can clearly see here that these angles are on the same chord, right? In the same segments.
Okay. And one of the important things, you have to be able to visualize it because in the exam it can be confusing with a diagram. So if you need to put in your own chord, that is fine. If you need to put in your angles and spin it and turn it a different way, that's fine. You will see angles on the same chord for yourself if it is that you do it in a way that you understand.
Hold on there. Mr. Brown said that really quick. Exam tip. Guys, write it down. Exam tip. If it is that you don't see it, add it to the diagram. We need to make sure that you're clear on what you're doing. So if you don't have the chord, just simply put a little line in it, spin your paper if you need to see whatever you need to see. Write that down. That's an exam tip, guys. All
Okay.
right.
I hope everybody got that.
Yeah, man, them get it, man. Them have them paper, them get it.
Okay, let us move into another concept related to circle theorem.
Wow, big word. Cyclic quadrilateral.
Cyclic.
Oh, wow.
So when you hear the word cyclic quadrilateral, what comes to mind, Brittany?
All right. Well, guys, let's start off with what I know. Now, what I know is I know what a quadrilateral is, right? So I know that a quadrilateral is a four-sided figure. Now, cyclic, on the other hand, let me just go a little
What does
deeper.
it
Let me
sound
dig.
like?
Well,
I'm
it
thinking
kind of
like
sounds like a
bice.
circle.
Yeah,
It sounds
something
like a
cycles.
Yes, and we know water cycle goes around. So I'm
Yes.
thinking it's something that goes around and it has something to do with a four-sided figure. I just putting together things that I would have known from other places. Mr. Brown, I hope I'm right.
Okay, that is right. And the most important thing, the vertices of the quadrilateral must stand on the circumference. That's an important concept in identifying the cyclic quadrilaterals.
All right.
So let us look at these and see if we can identify some of them.
Okay. Boy, you come out strong this morning though. All right, let me see what I can do. You said the vertices must be on the circumference of the circle,
All
right?
the vertices
all
must.
all the vertices.
Yes.
All right. So right there and then, guys, it eliminates 3 for me. Right? Because all the vertices of the quadrilateral in 3 are not on my circumference. So 3 is out. So for me, 3 is out. Mr. Brown, 3 in or out?
Definitely out.
All right,
Because
so
I'm
3 is
only
out.
seeing 2 vertices on the circumference.
All right. Process of elimination. I have to go take it from the out and then go into the in. All right. Let's look at 4. I realized that with 4, one vertex is not touching my circumference. So in this case, one vertex is not touching the circumference. So 4 is also out. Right, Mr. Brown?
I'm agreeing with you. But what do you think about 1? Because 1 has it looks a little bit funny.
One kind of specialist for true. Okay, guys. So I'm not too sure about this one. I'm going to go out on a limb, and I'm going to check back. You said 4-sided figure. All the vertices must be touching my circumference. You know, I don't know if I'm right, but I'm going to say that 1 is in because all of my vertices are touching the circumference.
And I'm agreeing with you. That is awesome, Brittany.
Wait, so hold on. What about 2, sir? It's in or it's out?
2,
Yes.
and almost 8. I am seeing all of them on it, and that is easy to see that all the vertices of 2 are on the circumference. That's a given.
Oh, so one was the hard one. You come trick me. All right,
Yes.
it's okay.
Okay.
It's okay.
Okay. Let's do some exploration. Wow, Brittany, I'm hoping that you're seeing something special.
I think okay, guys. I think I see something, and hold on. Yes, but definitely. See clear. Yes, yes, yes. So, Mr. Brown, you ready to hear what I see? I'm very excited.
Oh, okay. Tell me what you're seeing.
All right. The first thing that I'm seeing is that opposite angles in my quadrilateral, they sum to 180 degrees. Because when I look, angle F 111 degrees and angle E 69 degrees, that sum up to 180 degrees, right?
Okay.
So I'm looking and I'm realizing that opposite angles sum to 180 degrees.
Okay. Okay, and that is good. But look at what happens now when it is no longer a quadrilateral.
Yeah, man. So when it's no longer a quadrilateral, what happens, Mr. Brown?
You're realizing that we are getting different values. That relationship no longer holds.
So it no longer holds. All right.
Oh.
But Mr. Brown, let us hold on to that just a second, right? Let's hold on. Let's go back to something, right? Let's look back at something. You know, sometimes, guys, you know how it goes, right? You don't remember. So, guys, let's look at something right here.
Oh,
Right?
I'm seeing it.
Let's look at number 2. Let's count the vertices that we have. 1, 2, 3, 4, 5. So look at how you can get catch sometimes. Right. So this is actually not a quadrilateral, but a 5-sided figure. No, it caught me. It caught you.
It caught all of us.
It mashed up Mr. Brown. Look at that.
It caught us.
So
we were just so overconfident and so overjoyed.
Right.
Because we learned this new concept and didn't realize that this is not a quadrilateral.
So number 2 is actually out. It's not a quadrilateral, right? So it's not a cyclic quadrilateral. Guys, it happens to all of us. This is the reason why you should review in your exams. So you should always go over the question and don't be overly confident, because you saw what happened to us, right? Sometimes you're overly confident and miss the small things. So another exam tip, right?
Oh, okay.
All right, so let's continue on.
It's, to be specific, it's a pentagon, right?
Yes, it's a pentagon.
Oh, okay. Just that we recall what we were doing. Okay. So we looked and we realized that the opposite angles in a cyclic quadrilateral had a special property.
Yes, the opposite angles actually sum to 180 degrees. Well, that was my observation. And I think you're telling me that I'm correct.
Yes, and that is basically what we were seeing. And we established this before in terms of cyclic quadrilaterals have all the vertices line on the circumference, and that the opposite angles sum to 180 degrees. They are supplementary. That's the word we use in math.
Oh, yes, that is true. I remember my teacher telling me that one time that, you know, when angles sum to 180 degrees, they're supplementary angles. Yes, I remember
So
that.
sometimes they'll use that word supplementary. Just recall that means they sum to 180 degrees. Okay? And here's another one. Identifying the same property, right? So we're seeing it holds true for a number of cases. And we would have done the exploration to show you before. Wow. I'm hoping you're all seeing it. We have different cases, different quadrilaterals in different positions, And this property holds true for all of them.
So opposite sides in a cyclic quadrilateral add up to 180 degrees.
The
Guys,
angles.
the angles sum to 180 degrees. Please write this down. I hope that you have out your pens and your papers and you're taking notes. So take notes, guys. Remember, you have to flip back sometimes because you don't remember, right? So write it down.
Okay. So let us look at an example. So here we have a quadrilateral. Let's confirm so that we don't make the same mistake
All right,
again.
so let's see how many vertices we have. 1, 2, 3, 4. Yes, it's a quadrilateral, sir.
And are they all standing on the circumference?
And they are all on the circumference of this circle.
Okay, so we are confirming that this is indeed a cyclic quadrilateral.
Yes, sir.
Okay. So we have some values now entered in our cyclic quadrilateral. We're given 130 degrees, and we're asked to find the angle marked X.
All right, okay. So this is putting what you learned into action, right? Okay, so we know that opposite angles in the cyclic quadrilateral sum to 180 degrees. These angles are supplementary, right? All right, so that's point 1. So if they sum to 180 degrees, and I know that one angle measures 130 degrees, then 180 subtract 130, you thought you could trick me. Guys, it's 50 degrees. So this angle measures 50 degrees. Sir thought he could trick me. I think he thought he could trick you at home too. But no, we got this.
We got this. We got this.
Yeah, man.
So X is 50 degrees. Okay. So just to recap, opposite angles in a cyclic quadrilateral are supplementary.
Guys, you realize how many times we're recapping? Same amount of times you should be recapping too. Make sure you're looking
at it. It helps
back.
you to remember them.
It does. It certainly does.
Okay. Let's look at this one. What can you tell me about this one?
Okay. Wait a minute. So me have to pause now. Sorry, you're going on with a few things here. So I am seeing a cyclic quadrilateral. So I'm seeing a quadrilateral inside of a circle. I'm seeing 3 angles. I'm seeing one angle that lies on a straight line. So I'm seeing that Y and W lie on a straight line here.
So they are supplementary.
So they're supplementary. And I'm also seeing an angle at my circumference, angle X. Okay?
So we're trying to identify some of the relationships here between angles X, Y, and W.
Oh, Lord. Sir, come for me. Oh, gosh. All right.
So let's see what we can do.
Oh,
let's start with X and Y.
X and Y. All right. This is one thing I know, and I know that I know that I know. I know that X and Y are supplementary angles, sir. Am I right?
Yes. So
okay.
X plus Y would have a value of.
So X plus Y would sum to 180 degrees. So I know that. What I don't know is I don't know the value of W. But you already pointed out a very important property, that angles that lie on a straight line, well, they also sum to 180. They're also supplementary, so they also sum to 180 degrees. So guys, sometimes you may see something like this, and you may say, oh my God, I don't know, I don't understand. You actually have the knowledge. Just go back in your memory box and pick up on some things that you already know. So we already know about angles on a straight line. So don't get nervous, okay?
So if I gave you the value for X, you would be able to find everything from there.
Sir, I could mash this up. 1, 2.
All right.
I got this.
Let me
you got this too, guys.
Okay. So we're going to take our final break. When we come back, we'll wrap up things. Welcome back. Let's continue our lesson. So, Brittany, we were talking about this diagram when we left. So let us wrap up in terms of finishing our discussion. So, for example, if I gave you the value of the angle x to be 70 degrees for argument's sake, would you be able to find the rest of the values?
Okay, so guys, watch Michelle learn this question. All right, so if I know that angle x, you said?
Yes, it's 70 degrees.
If I know that angle x measures 70 degrees, guess what I also know? I also know that angle w measures 70 degrees.
Whoa.
You see, you didn't see that one coming. You didn't see that, right?
Tell them how you got that.
Okay, so guys, let's think about it now. If we know that the angles lie on if we know that angle w lies on a straight line and we know that x and y would sum to 180 degrees, then automatically the value of w and the value of x would be the same value, right? So they would have the same value. So I know that w would measure 70 degrees as well, and I know that y would measure 110 degrees.
That is so awesome. I'm very proud of you.
Pop my color, because sir never know I would have known that answer.
Okay.
Look at that.
So, look at this. I'm hoping you're able to see. So that is basically what it's going to boil down to. So once we find, we don't necessarily need to go through the long method of actually using this to find that, because we know the relationships are supplementary in both situations. So we know that this angle,
whatever the value of angle C is, which in this case,
yes,
angle C was 85.46 degrees. Whatever that value is, angle E would have the exact same value, right?
Yes.
And that was because of all the properties that were listed before. So guys, a little exam tip. Don't stress out about certain things. You have the information. So once it is that you have that information, use it. Don't freak out. This doesn't look like something that you'd see regularly, but it actually is something that you know, right? So once we know the value of angle C, we also know the value of angle E.
Okay.
All right.
That's awesome, Brittany. So let's move into our last theorem, or alternate segment theorem. So let's see what's happening with this. I'm hoping you're seeing a tangent to the circle at point C.
Yes, I am.
At angle C.
Yes, it touches the circumference at only one point, right?
Yes.
Okay.
And angle C is formed between the tangent and the chord CD.
Oh yes, I'm seeing that. I'm seeing it. But
So let's see what you can pick up.
This is interesting.
Sorry.
No, one of the things that I noticed is that angle C and angle E always had the same angular measure. What? No, I don't understand. No,
And
this math's really... This is really something else. Wow. Okay.
Okay.
So, guys, as you can see, you saw we moved around, we moved all over the... So there's a little relationship. What's happening, Mr. Brown? So yes. So that's what I observed. I don't know. Is there something else I should have seen? Is there something else I should have seen?
No, that is it in terms of being in the alternate segment. Once an angle is formed between the tangent and a chord, the angle in the alternate segment has the same value.
Okay. Okay. All right. So that's an interesting and important thing to note.
Okay. Okay, let's look at this question.
So again, guys, hope you're taking notes. The angle between a tangent and a chord is equal to any angle in the alternate segment. So again, I know we said it, but this is just for repetition and for you to write it down. So for you to have some notes as we go through our lesson.
And you're seeing it there. This angle 39 degrees formed between the tangent and the chord is the same as the 39 degrees in the alternate segment. So that's just formalizing the concept. And we're highlighting the alternate segment. So that is the only angle there that's going to be formed in the alternate segment.
So again, we're showing you the angle, 39 degrees. One more time, so many times we bring these things up. The angle between the tangent and the chord is equal to any angle in the alternate or opposite segment. Again, we're repeating it several times for you guys to take notes of this important information.
Okay, so let us look at...
All right, guys, so let us do a little recap of all of the theorems that we've looked at today. So we started off with the first theorem being what again, sir?
Angles at the center.
Angles at the center.
And we identified that relationship, the angle at the center being a specific relationship between it and the one at the circumference.
All right, so guys, there's a relationship between the angles at the center of the circle and the angle at the circumference of the circle. So we know that the angle at the center of the circle is actually twice the value of the angle at the circumference of our circle. So that was the first theorem that we looked at. What about the second theorem, Mr. Brown?
And we also looked at angles subtended from the same arc.
So angles subtended from the same arc. Wow, big words. What does that mean exactly?
Some persons say standing on the same arc, but once it is that the angle is formed by extending from the same arc, then those angles are going to be equal at all times. Okay,
so how about our third theorem? That was the one with the cyclic quadrilateral, right?
Yes, and that was angles, opposite angles in a cyclic quadrilateral are supplementary.
So opposite angles in the cyclic quadrilateral are supplementary. And the very last one, guys, which is the one we just did, was the alternate angle theorem, right?
Yes. And then finally we wrapped up with the alternate segment.
The alternate segment. Okay, guys. So that's all for this lesson. And today we looked at circle theorem. You can catch a repeat of all of today's lessons on JNN at 4 p.m. Highlights of the week's programs are also on Saturdays between 1 and 4 p.m. on TVJ and on video on demand on One Spot Media.
Remember our new times, Monday to Fridays, 9 a.m. to 10 a.m. And also the school time channel, 24-hour learning is back on One Spot Media. Until tomorrow, keep safe.
Bye, guys.
Bye.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.